In this next problem, we're going to transform a Y configured circuit to a delta one. And I realized when I started this problem that I think on the problem before that I did, if you watched that one, that I did not have this correct formula on the sheet for transforming Y to delta. We didn't use it because we were using delta to Y, but just in case you happen to notice that. So here is our problem. We have a circuit. We're supposed to find the voltage across the current source. And you can see we have a Y configuration there. It looks like a T, but a T is the same as the Y. I have the wrong formulas there. So we need to get the correct formulas. So let's go get those. So these are the ones that we need. So those are the formulas that we need. Let's see. Looks like I can't get rid of that little thingy in the middle. Well, I will live with it. Okay, now the important thing for me, at any rate, is to label my circuit. If I label my circuit, then everything is going to work out all right. So I'm going to label my resistors R1, R2, and R3. And I want to do it the same way I do it in my notes, except I can't read my writing. So I will just do my best and hope that I end up with the same thing. I'll call that R1, that R2, and that R3. Now I'm going to do like I did in the last problem, and I'm going to draw in a delta circuit that we're going to replace this circuit with. And if you remember, when we did this here, we had our same nodes A, B, and C for our delta circuit and our Y circuit, and we're going to do the same thing here. So I'm going to draw it in. Now, because it's shaped more like a T than a Y, I'm kind of going to move this node up a little bit. Let me draw that better. Okay, so that's R2. So the top part is like that, and then we have our side, and then we have our side there. So you can imagine, if you kind of close your eyes a little bit, squint, that looks like a triangle. And I want to give the nodes the correct name. So go back and look at what we have here. So R1 and R2 go with nodes A and B. So here's R1, so I'll call that A. Here's R2, so I'll call that B. And here's R3, so I'll call that C. So I just matched them up. R3, this was R3, so that went with C. This was R1, that went with A. This was R2, that went with B, which I think completely does not match my notes, which means I'm going to make some mistakes, and oh well. Okay, so now RA is opposite node A. So this is RA. RB is opposite node B, so that's RB. And RC is opposite node C, so that's RC. So now we can compute those values. RA equals R1 times R2 plus R2 times R3 plus R3 times R1 over R1. So that's 100 plus 200 plus 50 over 5, which is 350 over 5, which is 70 ohms. Hey, that matches something in my notes. All right, now notice that the numerator is the same for all of them. Just like when we were doing delta to y, the denominator was the same for all of them. So RB, I already know the numerator is going to be 350. And the denominator is R2, which was 20. It goes into 17.5 ohms. And then RC will be 350 over R3, which was 10, or 35 ohms. Okay, so now we want to try to redraw this without the Y resistors. So we now know what the equivalent resistors are for delta, so we're going to redraw it without the Y resistors. It's going to look a little funny, but we don't make fun of them. That wouldn't be nice. Okay, so let's see, RA was the one on top, and RA we said was 70 ohms. RB is the one on the right, which we said was 17.5 ohms. And RC was the one on the left, which we said was 35 ohms. Now let me just check my notes and see if that matches. And that does appear to match. Okay, so now we can see a couple things that if you look carefully enough, you can see that if you look at this end of the 17.5 ohm resistor and the 105 ohm resistor, and this end right here, those are connected. That makes these parallel. So our equivalent resistance, so 17.5 parallel 105, is product over sum 17.5 times 105 over 17.5 plus 105, and no, I am not going to try to do that. So 17.5 times 105 over 17.5 plus 105. 15. That's handy. Okay, so that is equivalent to 15. Now if we look at our two resistors here on top, they are also in parallel. So 28 parallel 70 is 28 times 70 over 28 plus 70. By the way, if you have been to any of my sessions, you know how much I like this calculator. It's actually in the United States sold as a TI-36 X Pro. The 30 is I think European. I'm not sure, but it does all kinds of things. But regardless of what kind of calculator you have, if you have a nice fraction feature like this, I recommend doing calculations like this using the fraction feature, because you can just see where everything is. You don't need as many parentheses, and you can just look and see, oh, okay, I've got everything right, because with all the parentheses, it's easy to make mistakes. I mean, I can make mistakes no matter what, but, you know, it's a little better. Okay, so that gets me 20 ohms. And now I can redraw this. So that's 2 amps. That one was a 20 ohm resistor, and that took the place of these two. This is a 15 ohm resistor, and that took the place of these two. Oh, curvy wire. Okay, and that one is 35 ohms. Okay, now you can easily see that the 20 and the 15 are in series. So we can just add those. And now you can see that these two 35 ohm resistors are in parallel. They're connected at their bottom ends and their top ends, so they are in parallel. And they have identical resistances, so the equivalent resistance will be half. Or 17.5 ohms. Okay, so now we can use Ohm's law to find the voltage. So V equals IR, or... Okay, so we have our voltage, we have our current is 2 amps, our resistance is 17.5, and so our voltage is 35 volts. So that would be the voltage across the 17.5 ohm resistor, and also the voltage across the 2 amp current source. Let's see what else they are asking. They are in parallel. And oh, that's all they're asking for. So 35 volts, and that does appear to match my answer. And so that's the problem.